Swayam Prabha. Digital India. Educated India.
I am not saying that I will. Don't allow me to mislead you on this last day of class. How did I write one earlier? Oh, again I have created some degeneracy. Now, theorem 2 is a little more complicated. And what we will do is we will only prove the positive part of it. The negative part you can work out by yourself if you are interested. So, what theorem 2 says is that if, what is this? What is this letter? Gamma. Gamma nu and gamma mu which kind of reminds me that we have, I know an eminent scientist who used to use, what do we write? We always write sum over ijkl, but I know somebody who used to write sum over mu nu delta alpha. Dirac also used to do that. Okay, it just adds a little more gravity to the situation. Okay. What are these? What do we write gamma for usually? Irreducible representation, right? Let us say these are two irreducible representations of order nu and mu respectively. And the reason why we take the trouble of writing nu and mu and all that is that we are going to use n for something else. Okay, that is why. And also it looks more serious. Okay. Okay, so let us say these are two irreducible representations of order nu and mu respectively, and let us say you have a matrix A such that A d nu r is equal to d mu r A. So, this is not commutation, right? This is not commutation. You have taken that matrix, you have left multiplied it, you have used it to left multiply d mu r, and you get d nu r, sorry, you get d mu r right multiplied by A. We are talking about two different representations, irreducible representations. What kind of matrix is A? Is it a row matrix? Is it a column matrix? Is it a square matrix? What is it? Square matrix? What is it, Kamal? What do you think it is? Triangular matrix? It cannot be. Rectangular matrix, right? Prolonged means, I think what you mean is rectangular. See, it's going to be square only if n nu equal to n mu, right? The orders are the same. If orders of the two matrices are the same, or rather dimensionalities of the two representations are the same, let us put it that way. Order, when we say order, we actually mean the whole group. So, if the dimensionalities of the two representations are the same, then and then only is A going to be square matrix. We are very comfortable with square matrix and with row and column matrices, right. We generally do not like to talk about rectangular matrices. But then the point is, if these two irreducible representations are of different dimensionalities, then A is going to be a rectangular matrix. Understand what I am saying? So, the general case is rectangular matrix. Special case is square matrix if the two dimensionalities are the same. Okay. Let me finish writing the theorem. If gamma nu and gamma mu are two IRs of order, actually I should write dimensionality, no? Cut, do not write all this, are two IRs. Nu and mu are identifiers, gamma 1, gamma 3, something like that, okay. And if A d nu r equal to d mu r A, then this matrix A is going to be non-zero if and only if n mu equal to n nu and det A is non-zero. This is what we are going to prove. Okay. It is a little more complicated than the first one, but we will stick to the simple part of it anyway. You have two different irreducible representations, gamma nu and gamma mu, and let us say there is a matrix such that A d nu r equal to d mu r A for all symmetry operations R. You cannot say that it works with one symmetry operation, does not work with another, that is no fun. For all R's, then A is non-zero if and only if the two dimensionalities are the same and det A is non-zero. Okay. And since we are writing A here, that is a hint that this A also has got something to do with the A that we used earlier, right. This is a little longer than the previous one. To start with, let me make an assumption. Of course, once again, whoever has done my class earlier would know that when you assume, what do? You often make an ass of you and me, right. It is there in the spelling itself. When you assume, you make an ass of you and me, okay. But see, science is all about assumptions that do not make an ass of you and me, right, intelligent assumptions, valid assumptions. So, let us try to make an assumption that will simplify the problem, but will not lose out on the generality. And one such assumption that we can make is that let us work only with unitary matrices. Suppose I say I am going to only work with 1 by 1 matrices. Then of course, the meaning of the word assume is what I said already. I am not saying that. I am saying that let us say that these matrices are unitary. Am I allowed to make that assumption? And this, in case it does not ring a bell yet, was our midsem question. Midsem question? Yeah. Unitary transformation can be done, right? It does not matter, take any representation and you can make a unitary transformation and generate unitary matrices. And then it is easier to work with them. And also, when you are talking about irreducible representations, you are going to work with these orthonormal bases, and then the transformation matrix is going to be unitary anyway. Remember? So, I think we are fine if we make this assumption that d mu r and d nu r are unitary, and we will see in a while how that makes our life a little easier. Okay. Let us go ahead. So, what we have said already is A d mu r is equal to d, I think we said A d nu r equal to d mu r A. Okay? That is the definition of A anyway. Starting with this, if I want to simplify, what we do is, first of all, let us take advantage of the fact that it is unitary. If I want to take advantage of the fact that this matrix is a unitary, what should I do? Whenever you have matrices, you somehow want to get to the inverse, right? Because matrix multiplied by inverse is in any case E. So, and in case of unitary matrix, what is the inverse? What is the inverse of a unitary matrix? Transpose is going to get you maybe 2 out of 5. Adjoint. Transpose and then take complex conjugate, or complex conjugate and then take transpose, whatever. Adjoint, right? So, what I would like to do is, let us generate the adjoints, because eventually you want to do similarity transformation. For that you need the inverses, and here the inverse is just the adjoint. So, let us take adjoints. I can write d nu r adjoint A adjoint is equal to A adjoint d mu r adjoint. I think we had encountered this earlier just before mid-sem when we did that unitary transformation discussion, isn't it? You take an adjoint of the products, they get interchanged. Okay? Now, these are all unitary matrices, right? Since these are unitary matrices, this d nu r adjoint is the inverse of d nu r, right? This is d nu r inverse of that, right? And are these any kind of unitary matrices under the sun? No, right? Because then we would not write R. What kind of matrices are you working with? Transformation matrices, right? So now you tell me, what is the inverse of a transformation matrix? Now we go from mathematics to chemistry. Inverse of transformation matrix is the transformation matrix of the inverse symmetry operation. Isn't it? Inverse of the transformation matrix has to be the transformation matrix corresponding to the inverse symmetry operation. C3V, C3 and C3 square are inverse of each other. So, inverse matrix of the transformation matrix of C3 is the transformation matrix of C3 square. Remember? Because when you multiply them, you must get the unit matrix, right? So, I can write d nu r inverse A dagger is equal to A dagger d mu r inverse, alright. And then I want some kind of a similarity transformation. For that I can either right multiply or left multiply. I choose to left multiply, so that I am going to do a similarity transformation of the left hand side. So, what you want to do is left multiply by, what should I left multiply by so that this left hand side becomes a similarity transformation? A, B, X, C, D, P, Q, what? A, right? Because this is the inverse of A. Not necessarily, but this looks at least something like a similarity transformation. A d nu R inverse A dagger is equal to A is not inverse, sorry, my mistake. It looks something like a similarity transformation, not actually. A dagger d mu R inverse. It will help us eliminate some things. So this is where we have reached. We have to remember this. A d nu R inverse A dagger is equal to A dagger d mu R inverse. Okay. Now we have started from R and we have reached R inverse. Right. Another way of doing that would be from here. This R is general, isn't it? It's any symmetry operation. So I don't think anybody will have any objection if I write A d nu R inverse is equal to d mu R inverse A. Isn't it? Instead of R I can write R inverse. Right? Now what do? I want to eliminate something, right? I can choose to eliminate this or I can choose to eliminate this. Let me try and eliminate this one. If I want to eliminate this, I want the same term in the second equation also. What do I have to do? See, A d nu R inverse is already there. And this is just A d nu R inverse right multiplied by A dagger. So if I right multiply this entire expression by A dagger, then the two LHSs become the same. Right? You get A d nu R inverse A dagger is equal to d mu R inverse A dagger. Right? So what do I eliminate? I eliminate this and this. And I am going to get A dagger d mu R inverse equal to d mu R inverse A dagger. Right? So what is that? That is commutation. Isn't it? Commutation. A dagger d mu R inverse is equal to d mu R inverse A dagger. Right? Okay. Don't forget that a product of two matrices is a matrix in its own right. Just because I have multiplied two matrices, you should not think that what I have got is something different. It's a matrix. Commutation, right? And what was theorem 1? So this A dagger, I can call it maybe anything, I can call it alpha. So won't you agree that this alpha matrix is a constant matrix? Right? So which implies not much space left. A dagger is lambda into E. Okay? What is it that we wanted to prove? Let's not forget what we wanted to prove. This is not theorem 1, this is theorem 2. And theorem 2 is, if these are two IRs, and if A d nu r equal to d mu r A, then A is non-zero if and only if n nu equal to n mu and det A is non-zero. That is what we will prove now. Actually, we are almost there. So, what have we got? We have got A dagger, dimensionality, yes. So, what happens if n nu equal to n mu? What kind of matrix will A be? Circular matrix? Square matrix? And what about A dagger? So, it will be square of square matrix, right? So, 4-dimensional matrix, isn't it? That will also be a square matrix, right? So, both A and A dagger are square matrices. Okay? And we know already that A dagger equal to lambda E. So, what then is det A dagger? I will make your job a little simpler. Det lambda E let us talk about a 2x2 matrix, lambda square. Let us talk about a 3x3 matrix. Get the point, right? Huh? Lambda to the power n. Okay. So, this is going to be lambda to the power, you can write whatever you want, I will write n mu. I might as well have written n nu, it does not matter. But what about the left hand side? What is det A dagger? Will you allow me to write it as det A whole square? Huh? Just work it out, take any matrix, take its adjoint, right? Multiply them together, see what the determinant turns out to be. Work with a 2x2 matrix, it will turn out to be this. So, what is det A then? Det A is square root of lambda to the power n mu, right? So, if lambda is non-zero, lambda to the power n mu is non-zero, then det A is also non-zero, right? Right? And is going to have an inverse, and you are going to be able to write d nu r equal to A inverse d mu r A. For which value of r? For all values of r. So, that is the relationship between gamma mu and gamma nu then, right? What is the relationship? The corresponding transformation matrices are similarity transformations of each other, which means that gamma nu and gamma mu are equivalent matrices, equivalent IRs, sorry. What is it that we wanted to prove? two IRs, and if this, then A is non-zero if and only if n mu equal to n nu and det A is non-zero. We have proved the if part. We have not proved the on and only if part. We said if and only if, isn't it? So, if is proven, only if I leave it to yourself. It's not all that difficult. It's worked out here. It's the appendix of chapter 7. Look it up, you can do it yourself. At least we have proved the if part.